Students, welcome back to the part 2 of the lecture number 3. So, we have been talking about regression analysis, right. Regression is the first machine learning model in the category of supervised learning we discuss. And I give you some examples in the last lecture about the diffusivity and the temperature relationship. We know that the relationship is very well known, but to give you an example so that you can understand that. So, let us go back into the board and discuss what are the various aspects of this regression. So, regressions can be different types, as you understand, because we are trying to find out relationship between a dependent variable with an independent variable. So, first relationship we can talk about is linear, right. That is the first thing you can talk about, the relationship between y and x as a linear. In the last lecture I gave you an idea, y equal to w0 plus w into x, that is the equation of a straight line, right. And here you can write down this, you can plot that this is y, this is x, and depending on the value of x, w0 and w, you can have different kinds of straight line. So, this is your w0 and the slope of the line is what is called, this is the slope, that is your w. So, this is the equation y equal to w naught plus w in x. This is the linear relationship. We will talk about in detailed manner how we can handle it in terms of data, right. So, you can also have polynomial, right. You can also have polynomial. Remember, linear is the single order polynomial, right. Linear is a single order polynomial. Y is equal to w0 plus w into x to the power 1, the single order polynomial. So, you can have different kinds of polynomial possible, double, triple, third order, fourth order, okay, sorry, not order, degree, third degree, fourth degree, fifth degree polynomial possible, right. So, this is not order, this is degree, order is come in terms of differentiation, right, that is, please be careful about it. So, this is called degree of the polynomial. So, you can also have other kinds of regression analysis. One is called logistic regression, which is used in case of yes or no cases, logistic regression. You can have also ridge regression, and then you can have also lasso regression. We will talk about all these aspects in the next lecture. Today we will focus on linear and polynomial regression. So, I just wanted to give you different examples of regression techniques available: linear, polynomial, logistic, ridge, lasso. Some people call linear and non-linear also, but polynomial is a better term because non-linear can have different degrees. So, that is why polynomial is. So, the moment you talk about polynomial, linear comes also as a part of polynomial also, because if you have degree 1, it is nothing but a polynomial, linear polynomial. Okay. So, let us talk about linear aspect first. That is what we started with, linear polynomial, the relationship between independent and dependent relationship in terms of a linear equation. So, what is the best simplest possible relationship you can think about it, that I have written already, y is equal to w0 plus w into x. That is the simplest possible linear relationship between a dependent variable and independent variable. Okay. That is what you can think about it in terms of mathematical equation, linear relationship. Here w0 and w are the coefficients that we need to figure out from our analysis. How do we do it? Well, you can do it using what is known as a least square method. It can be used to determine w0 as well as w, correct. How do you do it? Let us talk about a little bit on that, how you can do that. So, we can do that very simple. Let us talk about, write that regression least square method. Okay. So, we can write down this as what? This we can write down simply as a summation, because it is like a data. I can go to 1 to n yi minus w0 plus wx whole square. This is what my difference of the output minus the input. What I mean to say is that if I take this one is my input, depends on x actually, w0 is constant, but still it is a part of the x side, and this is my resultant value. After I put the value of x, that difference is this, and then we take a square of that. Remember this, we take a square of that, that is what is called the RSS, what is known as a residual sum squares. This is called residual sum square. That is what is called RSS. What you have taken is difference between your resultant value y and the input, the portion because of the independent variable. So, this difference, then we square it. Now, you must be thinking why you are putting summation, because we have data in terms of x and y, x1, y1, x2, y2, x3, y3 goes on, right, xn, yn, correct. That is what we have. Now, these are my data, that is what I am using for fitting the model. So, that is why I have to sum it over. For each value of I am doing the sum it over. Am I clear? So, how do I find out the W naught or W naught and W? Very simple, simply by taking the first differentiation. So, let me remove this part so that I can talk about it. I can just differentiate this RSS with respect to both W naught and the W and put it 0. So, for minimum value of RSS. So, if you look at carefully, RSS is nothing but error, okay. This is nothing but error. So, by minimizing RSS, we are minimizing the error. That is why it is called a least square method. This is square, and we will find out what the least value of that. So, that is nothing but minimized RSS. So, there will be two equations possible. One, because there are two coefficients W0 and W. So, we have a difference with respect to W0 first. So, it will be sum it over I1 to n y naught, because remember this is square, minus W naught plus W into x. That is what it is. This is the first derivative of RSS with respect to W0, and this must be equal to 0, right. This will allow us to find out, if I put this as a 0, this will allow us to find out value of W naught, or basically it will allow us to get an equation between W and W naught, right. This is the first equation we can do. Then we can also find out same thing with respect to W. So, what you will get? You will get little different. First, you have to difference the square. So, that is what you will get this. Into x, you will get, this is xi, sorry, I am making a mistake. This will be xi, because yi is there, means xi will be there. This is my second equation. Wrong. Yeah, it will be xi, sorry, yes, because W is there now, this is correct. So, I get two equations. These two equations can be used to get the value of, find out the optimum value of W0 and W1, W basically. So, we can find out optimum value of W0 and W by simply solving these two equations. You understand that, right? That is very easy. So, we have this residual sum of square, this is the difference between output or rather dependent variables or labels minus effect of input variable x and square, and we try to minimize the square. That is what is called, that is why it is called a least square method. Many of you probably have used it in your aspects. So, that is very simple, right. So, how do I write in terms of matrix, because this equation is not very convenient when you are talking about data, right. So, we have to write in terms of matrix, so that it is understandable and doable very easily. Let us do that in terms of matrix, so that you can easily implement it nicely. So, I can write down this in terms of matrix n, remember this, I goes to 1 to n xi, sum it over I goes to 1 to n xi, sum it over xi square, I goes to 1 to n, okay. W naught W, this must be equal to sum it over yi, obviously I goes to n, sum it over yi square, no xi yi, because you have xi yi, right. I will explain to you. So, what you see here? So, you can find out easily the equations simply by that, n W0 equal to yi, correct. So, you can, this is simply a matrix way of writing the same set of equations, correct. That is very easy to understand that. So, you see here summation of yi is here, summation of y is here, that is why it is here, summation of yi and xi is here, xi is there, that is why it is here, okay. W naught is here, W is here, correct. So, W into xi yi plus W naught, that is the value of x1 actually. So, you can easily find out both the sets of equations simply by this way, very easy to do that. So, now for any inversible process, let us use this. For any inversible process, if the matrix can be inverted very easily. So, I can write down for inversible matrix, all matrix may not be invertible, okay. It is basically talking about transpose matrix, invertible. If there is a matrix M, if I can transport it to m to the power t, we can write down W naught and W as like this, n So, these are my values of W naught and W, simply in terms of matrix. So, you can clearly see that this is the easiest possible way of putting together an equation. Now, values of W0 and W are basically depends on what kind of data set you are using. If you, so finally what you will get? You will get an optimum value of W naught and W, right, and the equation will be then correct. So, for any given new x xi, I can find out predict yi. because I have now determined both these coefficient values after doing this analysis. So, that makes sure that this predicted values will be very close to whatever is known from experiments or calculations. This is the way you can predict it as best as possible. So, that is about the linear model is very easy to understand, okay? And sometimes your data will have errors also, right. So, it is not that always the data will be very perfect. So, if you have error, then the equation has to be little bit modified. So, in case of errors in the value of x I and y I, let us say error is epsilon. So, this equation will be little bit modified. Let me do that modification. So, y I is basically equal to w naught plus w into x plus error, average error. This equation is modified in a very simple manner. This will be also epsilon I, okay, this x I. So, y I equal to w 0 plus w x I hat means the average these things, what is called nu. So, w 0 hat, that is the average value of w or the best possible value of w 0, w hat, that is the best possible value of w x I and epsilon I. If you want to incorporate error into your analysis, okay, simply it will have a new column in the matrix other than these three. Okay. So, therefore, this is the mathematical analysis of regression, how it can be done. Am I clear? Now, linear works very nice, but most of our problems are non-linear type. It will not work, and the linear model may not work. So, how do you take care of non-linear model? Let us talk a little bit about that, and what is called a polynomial model. So, this is, I would say, the whole regression analysis here we discuss is linear type, right, and that is why equation is just like a straight line. Okay. Y is equal to mx plus c, right, all of you know the linear expression is y is equal to mx plus c. So, here we write in other way, we write first the c plus mx, that is what we have done, y I is equal to w 0 plus w into x I, correct, that is exactly same. This is what we are trying to do, but in a non-linear case it will be different, or in a polynomial case it will be different. So, for the polynomial one, let us talk about that in the next 5 minutes or so. For the polynomial one, polynomial regression, we write the equation in terms of a polynomial. General polynomial equation is what? So, y is w 0, w 1 x, w 2 x square, w 3 x q, goes on, right, w n x to the power n. The generalized polynomial equation, general. So, in case of linear, this becomes like this, we truncate after first two terms. In case of quadratic, it becomes like this. In case of cubic, it becomes like this. What you are seeing is that this power on the x is increasing 1, 2, 3. That is what is happening. This is how the polynomial goes on. So, you can keep on writing different polynomials, and in general you can write down this polynomial, which is nth degree polynomial. You can see n degree polynomial. So, that is what it is. So, therefore, the problem here is, if you talking about quadratic, you have to find out values of W0, W1, W2. These are the coefficients. If you are talking about a cubic, then you have to find out W0, W1, W2, W3. So, complexity increases basically. Basically, you need to optimize the values of these coefficients, and you have to obviously use same thing what it is least square method, or there are many other techniques, but least square is the best technique possible. So, that is how actually one needs to do that. But remember, this is in terms of x. You can have other kinds of polynomial also, right? Like you can have, you can see you can have logarithmic type of polynomial, you can have exponential type polynomials, you can have even inverse type of polynomials. All kinds of polynomials are possible. Am I clear? So, how do you talk about different kinds of polynomials in that sense? That is the biggest question. You have to remember that. Very, very important aspects of that. So, in general, so I write down this equation in general in a matrix format. In a matrix format, this equation can be easily written out like this. So, y, which is nothing but y1, y2, y3 till yn is what? Is equal to like this, 1 x square to the power x to the power n. This is 1 actually, x1, then 1 x2 square, x2 to the power n, 1 x3 to the power square, x3 to the power n, 1 xn, let us not write xn, let us like xm, right, multiplied by all the w's, w0, w1, w2, w3, wn, and if I am considering errors, this will be epsilon 0, epsilon 1, epsilon 2, epsilon n. This is what it is. So, this is nothing but a y equal to x w plus epsilon, but here x has different degrees, right, that is what it is, x has a different degrees. This in general the polynomial looks like. So, if you just want to fit polynomial, let us say these are my two data, come back to the projection. You see there are two types of fitting of the data. You can see here this is fits nicely with the second order polynomial. That means what? Y is equal to w naught plus w1 x plus w2 x to the power square, and this one y w naught plus w1 x plus w2 x square plus w3 x cube. You can clearly see fitting is very nice, but look at the next plot. Say which is the best order to fit? 2, 3, 5, 2, 5, 8, 11, 14 and 17. Which one is the correct one? Obviously, if you are using very low value of order 2, it is underfitting. If you are using very high value, it is overfitting. So, there must be a way to handle this problem. So, this is very, very common in machine learning, overfitting and underfitting, mostly overfitting. So, how to handle that we will talk about in the next lecture. Thank you.